Banjo.
That's one of the things I need to do on my bucket list. I don't have a lot left. I really want to learn how to play the banjo. Okay, so let's talk about this concept of harmonics and how it plays out basically with different instruments. So, if you've ever played like the banjo, the guitar, anything like that, one of the things you can do to tune it is that you change the tension on the string. So, you got this equation that the frequency of the tune fork is the velocity divided by 2L, and L is length. So this is why, like, if you strum this note, okay, but then if you shorten it up and you divide and you're shortening that length more and more and more, you're not changing the velocity, and that is not, listen to me very carefully, that is not the speed of sound. That is the velocity of the wave on that string. So this is why if I go like this, okay, you have a certain frequency, but then if you shorten that up, then because you're dividing by a shorter and shorter value of L, that frequency goes higher and higher and higher. Now, this is the equation. The other thing you can do is a little bit of substitution. So to get the velocity of the string, that's tension divided by mu, and mu is this mass per unit of length. So the other thing that you can do beyond changing the length of that chord is that you can change the, which one this is, okay? So as you change the tension on the string, you change that harmonic, okay? So if you look at this in terms of tension, which is up on top, so as I was tightening that and increasing the tension on that string, that made that frequency go higher and higher and higher. So when you play any stringed instruments, basically you tune it by changing the tension in the strings. That adjusts the frequency. But in terms of the frequency that vibrates at, this is why you have those different frets, and that changes the frequency of the pitch that's going to be generated. Now, when you have the other type of musical instruments that involve sound, basically the wind instruments, so this is what we talked about, and this is going to be the basis of the lab that you're going to do today. So if you look at how this whole idea of harmonic plays out, so if I take this, and hold this over it, you're going to reach that point, okay, where it gets really loud. So this is a different situation. So basically what's vibrating is not a string. So when that string vibrates, that's going back and forth, and that's sending out compression and refraction waves. As a wind instrument, you're making the sound, the air inside of that reach a harmonic, where that reinforces itself, where you have like an amplitude meeting an amplitude, or constructive meeting a constructive. So when that happens, when you reach that one point, because it's an open-closed system, and it's the reason that we call it open-closed is that's what you're going to do in most of your lab today. That's a situation where it's going to hit here, it's going to go down, hit that, and if you hit that just right, it's reinforcing itself. So part of this is when you look at what's going to happen with like a standing wave. So if you remember back what we did when we started this, Pop and I had ends of that spring. And we would sit there and we would make that simplest harmonic, where that was as simple of wave as I could possibly get. It was just going very rhythmically back and forth. Yes?
This might be dumb, but like, what's
when they ask what's a standing wave, like what is a standing wave?
A standing wave is just that, where it's
That's it?
where
Even if there's
it's-
what if
where
there's
it's-
more?
Yeah, so
It can still be
the
a
other
standing
standing
wave?
wave would be something like this.
So it doesn't matter how many nodes
No.
or antinodes it has?
No.
Okay.
There's a standing wave. Mother Nature likes that standing wave. So I couldn't build a standing wave where I had something like this, where it would like hit and like be like a wavelength and a half. Okay? It just wouldn't work because Mother Nature goes, oh, this is just going to be weird, because if you try and send that down, it's not going to fit. So whenever you make that vibrate, it's only going to vibrate to create a standing wave.
So it'll like reach a point, it'll try and get to something so that the ends are like,
Yes, so your ends will be like your nodes.
okay.
So you can get something like this, and I'm just trying to guess where that's going to be, okay? So you could have something like that, but you couldn't have something like that, where it would end up like at a wavelength and a half,
Okay.
or a third, or something like that. That's what it's meaning by a standing wave. And so that's what happens with a stringed instrument, is that you create a standing wave based upon a certain tension on a string. And if you change the tension in the string, that changes the condition and you get a different standing wave. Same thing is true of a wine glass, okay? When I had that wine glass, and it would vibrate at a certain standing wave. And if I added water or took water away from it, that would change the conditions and we would get a different standing wave pattern. Okay? Does that make sense? Okay. So,
No idea.
On-
So what are we even talking about right now? Mr. Burkamp.
What?
So it physically cannot have a non-standing wave.
no, it
Oh.
won't reinforce itself.
So, and then another question, can you create like can you like create a deconstructed wave with that tube or not?
No. It's
Why not?
well, you could, but it's just like, so if I get like this, okay, it's making noise, okay, because what's happening is that it's still sending that wave down and it's bouncing off, but it's not lining up where like a compression meets a compression, okay, or the wave crest meets a wave crest. So, but it's just jumbled, right? So, but as I change and lift that up, okay, then I reach that point.
Wait, so is the water just giving it something to bounce off
Yes,
of?
all the water's doing is allowing that, is sending down a compression wave of sound. It's hitting the water and it's bouncing back and it's reflecting back up.
And then that's like the construction is when it gets to the, when we
Yeah,
hear
so
it?
when you hit that point of resonance, okay, what's happening is that basically,
Can you draw the resonance? I'm confused on what you're trying to say.
well, here's the anomaly.
Because like that, yeah, especially the construction, deconstruction, I'm so confused on that.
Okay, so when you have constructive interference, what happens is that you send a wave, I send a wave going down like this, okay? And you send a wave coming down in this direction like this. So when you have constructive interference, these waves are, you have the wave crest on both sides of the string. And when they meet, they're going to reinforce each other. So that's constructive interference. When you have destructive interference, is that I send a wave down on one side, you send a wave down on the other. And then when they meet, they cancel each other out. So this energy here balances out that energy there, and there's no net energy because they're going to cancel each other out.
Okay.
So what you hear, okay, that doesn't get very loud because they're not in phase when they're meeting each other. But when you get that point where it gets really loud, what's happening is that these are now in phase. So basically, that wave going down is exactly when it bounces out, when it bounces back up, then it's meeting another compression wave on the way down, and they get really loud. Okay? So if you could completely cancel them out, you wouldn't hear anything, but that's really tough to do because the air is still vibrating within that. Fisher?
So on the constructive waves, after they pass, they split back and
Yes.
just continue going. On the deconstructive waves, do they do the same thing, or is
Yes.
it? Okay.
Exact same thing.
I was just wondering if they canceled
How
out.
how is a standing wave not deconstructed? Because when you drew it, it looked like it was up and down at the same time, right?
No. So what's happening, and that's the weird way of trying to draw waves, Louis, is that when you, we'll just stand one up. Sorry, I'm drawing.
Also, if they're meeting for the constructed one over there, how come we can keep hearing it, loud?
Hold on, let me get into that, then we'll go back to sound. Okay, you got it, Pop?
You got a lot of questions.
I know. Okay, are you ready? So if I just so what's going to happen is that if you look at this, right? So this is one entire wavelength. So notice here, it's not moving on Pop's end. It's not moving in the middle. And mine is just because I have to generate that wave. So you have nodes and you have antinodes. So antinodes is where you have your maximum. So what's happening here is that this is one entire wavelength. So if I change that frequency, okay, notice that the only thing I can set up, no matter what I do, the only thing I can set up is a standing, whoa, throw that back. Oh! Go on. There we go, nice. So now, if I change the system, okay, like if I increase that, no matter what, the only thing I can set up is some type of standing wave pattern. So I can't set this up where like I have a half of a wavelength coming here. So this thing is only going to establish standing wave patterns because that's the simplest form. So if I try and do something wonky, even if I try to, okay, I can't get something other than a standing wave established. So what's happening is that when we do that wave and we change that, when that gets really, really loud, that's like, let's say this is just kind of random, whatever, haphazard, whatever, right? But then when it gets really loud, that's what I've done is that I've established that standing wave. So what's happening is that energy, if you look at just one, okay, so if I just have one at a time, that energy is going down. It's going to hit Pop and it's going to bounce back. So what happens is that when I establish that standing wave, then that energy going that way is being reinforced by that energy coming back the other way. And they're meeting in phase and they're not canceling each other out. Okay? Does that make sense? Okay, all right, let go. All right, back we go. Don't get over. It's tough to get off the ground. So here's the dichotomy when you're going to deal with this lab. Like when we have that situation where here's the tube and here's the water, we draw it as a longitudinal wave, okay? Because that's a good visual. That's not actually what's happening. It's actually a transverse wave. But it's really tough to try and draw a transverse wave. So that's why we draw it as a longitudinal wave, because, that makes it easier to see the value of the wavelength. So when I do this, and you get that point right there, so that's what was happening back there. That's creating the strongest standing wave. So what's happening is that when you measure this, and this is what we'll talk about in the lab, on an open-closed system, this is the leap of faith that that's what I tried to draw yesterday. So if you look at it horizontally, and I don't want that one aligned, you do something like this. So this is coming in here like this. So imagine you extend this wavelength out like this, where you create that standing wave. So we draw it like this because what this is representing is 1/4 of the wavelength. So this is going to happen here, and then if I could lift this up high enough, you'd actually get another harmonic when you would get to this point, because that would also reinforce itself. But that's harder to hear because that energy is getting more spread out. So when you find this first loud wave, what you're assuming is that is 1/4 of the wavelength. So to get the entire wavelength, you multiply whatever that length is by 4. Okay? So on that back side, when you get to like question number 26, where I think that's an open, is that the one with like the dinosaur? Which one has a dinosaur on it? Is that 26? Okay. So on 26, what they're saying is that, okay, if you're going to make noise as a dinosaur, okay, and again, you have to decide, is it an open system or is it an open closed system? So if you want to find this, so this is like, what was the length? Like 1.5?
Yeah.
Okay, it's fairly decent. Okay, that's like 1.5 meters. It's about like that. All right. So because it's an open closed system, to get the wavelength of the wave itself, you're going to take 1.5 times 4, and that's going to get you the entire wavelength itself. And so they're trying to find what you call the first fundamental frequency. So any velocity is wavelength times the frequency. And this is what we're going to do today. So I'm going to take 1.5 times 4. That's going to give me my wavelength. You know what the speed of sound is. That's 343 meters per second. You're going to solve for the frequency. So that first frequency on 26 should be around 60 hertz. Okay? Around there. Now, on an open closed system, you work on the odd numbers. It goes 1, 3, 5. Open system goes on every harmonic, 1, 2, 3. So to get your answer for that third harmonic, you're going to take that first harmonic and multiply that by 3. So let's say that first harmonic is 60. So that second harmonic would have a frequency of 180. The next harmonic would be, you're going to multiply it by 5 because it goes on odd numbers. So roughly on 26, your answers are going 60, 180, 240. Okay, that's an ish, but that's kind of where you're at.
So that would happen if you would raise that tube out of the water enough?
Yes, if I could lift this up to get 3/4, and I'll try it, but it generally gets pretty weak. So there's the first one. So if I lift this up high enough, if I don't run out, you can kind of hear it right there. It gets a little bit louder. So that would be like 3/4 of that wavelength. The first one's the easiest one to hear because that's the loudest. But then if you go farther up, yeah, you could pick up there. But it's because you have more air that's vibrating, it's tougher to get that actually just in phase where it really gets loud again. So yeah, so that would be like that third harmonic. Okay? Does that make sense? Okay. When you get to 22, don't make 22 complicated. Okay? Literally, do not make 22 complicated. Your answer to 22 should be around 400 meters per second.
22?
Yes.
What about 20?
Huh?
We should do all the evens. You should give us hints.
On 20,
Is it around 400?
Is it around 9?
22.
20. Around 9?
20 is around 9. and around 4.5.
Okay.
10 is around 40. 8 is around 2.
Before we get off the assignment, can you go over number 7 on the questions?
Yeah.
Wait, is it closer to 1?
Folded.
On 8?
Yeah.
No, it's closer to 2 than
Oh
it is to 1.
man.
Oh, you
Oh,
folded each
yeah.
one.
Can we? Can you do that one?
Let's go through the entire assignment.
Let's just do the whole
No,
time.
I feel like that wouldn't help.
No, that would really help. I'm
Wow.
struggling.
I'm gonna
On which
have to-
one? Number 8, Marilla?
Yeah, Zach failed me.
Well, that's your problem is you listen to Skippy. Okay,
Yeah, that's what I was.
so so this is like what we just did with Pop, okay? So here's the deal, you're 3 meters away, right?
Yes.
Okay? And you begin shaking the end of the cord at 3.5 hertz. So imagine me doing a vibration of 3.5 per second. Okay? So you have your frequency, right? Continuous sine wave length of 1 meter. So what that means is that if you were to come in here, and so let me draw one wavelength. Okay? So that would be one wavelength of 1. Okay? And then you'd have another one like this, okay? And then you're going to have another one like that, okay? So you're going to have 3 wavelengths like that. That's what I said. You can only set this up where it's going to reinforce itself, okay? Just what I did back there. So then, how much time will pass? The standing wave fills the entire length of the string. So if you look at what happens, how this begins, you start with sending this wave down like this. So the first thing I've got to do is that when I first do that,
Okay.
that energy has to go down the length of that wave. And then it's got to hit and reflect back and come back. So what's the total distance it's going to travel?
6 meters.
It's going to travel 6 meters.
Huh?
Okay?
Where did you get that from?
Because you're told that you're 3 meters away from the wall.
To make a whole wave is 6?
Yeah, because it's got to travel down, bounce off that wall, and come back.
Okay. I'll take your word for it.
Okay, now, you know velocity equals wavelength times frequency,
Yes.
right?
Uh-huh.
You have the wavelength.
3.5 and 6.
No, the
3?
wavelength.
I know, 3 point... Oh, wait. 1 meter.
So what's your velocity?
3.5 meters per second.
Okay, so what's the total length that it has to travel?
6. Okay, gotcha. Thank you.
So if it's
Wait.
got 3, like 3 frequency?
Well, this would be like the third harmonic. But don't get hung up on that. Okay? The whole point of this question that you understand is that when I first send that wave signal down, it's going to travel, hit pop, and then bounce back.
Gotcha.
Okay? So what's
So-
going to happen is that I'm going to send another wave at that same time so that it matches up. So this has to travel 3 meters down, hit that, and come back. So you know your initial wavelength and you know your initial frequency. That tells you how fast that wave is traveling down the string.
Okay, and your initial frequency is
3.5.
3.5?
Yeah, because that's what you're told that in the problem.
Oh, okay.
So I should take my distance divided by my speed? I
I
think so.
refuse to answer that
I
question.
think so. I think I had it switched.
I absolutely refuse to answer that question.
Okay, that's fine.
6 divided by 3.5 meters per second.
It's just
Yes,
one-
I
it's
just did
so
that.
It's just 1
I was
times
just making
3.5?
sure.
Huh?
It's just 1 times 3.5?
To get your velocity.
Yeah. What are we trying to find?
5.
Oh, okay. And then,
You're trying to find the area of the osprey, dog.
So then you take 6 meters divided by 3.5, and that's your distance.
Yeah,
Okay, gotcha. I think, cool.
but then the osprey comes down and swoops up the donkey and flies off with it.
Yeah, so you add 10. That's
I mean, yeah, and then you multiply by 10 decimals. What, Vitor?
I had questions on number 5. Like,
Question or problem?
Problem. Oh, no, question.
question 5. It's like, so how would you explain that if your vocal cords inflame?
Okay,
Like, that would decrease the
Big
pitch,
brain
right?
moment. I need to know.
Like, that would
It's just the mass
Decrease pitch?
increasing.
Yeah, it's their big.
Why?
okay.
Connor,
Our area,
I
not
just-
mass, but.
I said decrease in
understood all
pitch
the
because I looked it up and it said your
Yeah.
Oh
voice
my God, I
goes
know this
hoarse,
from
so.
Smart.
Okay.
I'm doing that.
So this mu
Big brain.
is that mass per unit of length,
oh, that's what we did, bro.
There's
okay?
the stuff that can like kill you.
So here's the story. When your vocal cords are inflamed, what's going to happen to that value of mu?
increase.
Increase.
So you're going to be dividing by a,
Smaller number.
Bigger
Bigger
number,
number
which decreases your
gives you a small.
Bigger
volume.
number.
Bigger area.
and decreases the frequency.
Which
Yes.
decreases the.
Wait,
V.
what? I did not do that.
Wait, so it just increases the mass when you're swelling because of. Okay.
yes.
Mass?
Oh, it increases the
Wait, can we
mass?
also use the intensity equation? You said that was fine earlier.
Which one were you talking about?
5? I said inflammation will cause your vocal cords to possess a larger area, which will cause the pitch of your voice to decrease since intensity equals
I
power over
thought you
area.
were talking
that
about
problem
this
sucks.
equation.
No, I was talking about intensity.
No, that had, no, you can't do that.
Another question.
I thought when you asked that, I thought you were asking about using it in this equation. Okay? When you said it's gonna increase the area, that's what I thought you were referring to.
Is there even area in there?
Not really, but it
Oh, okay.
increases the mass per unit of length.
You increase.
Vitor,
Mu.
On 7, well, the first one is just asking for like, what are the harmonies?
on problem number 4 or question 4?
Question 7.
Question 7. Okay, so we had that all screwed up. Question problem? I don't know. Okay, so on question 7, if you look at that, you have 1, 2, 3, 4. So what that means is on this one, 7, what's the mode value of m standing wave of this? So that mode is your number of antinodes. So on that one, that's just going to be 4.
4?
Because it has like 4 antinodes. You have 5
Antinode.
nodes, 4
When
antinodes.
was it ever said what an antinode is?
Huh?
Antinode. When have we ever been told what an antinode
It's
is?
in the book.
Wait,
Yeah.
so
It's in the it's in the thing right before this. It tells you.
Yeah,
Antinode
it
or no?
literally,
Yeah, it says m equals 1, 2, 3.
yeah.
And so would that be horizontal then? That would
Yes.
be, right?
Oh,
Why?
Which one?
7.
What?
Wait, why is it horizontal? Break it up.
Yeah, why is that?
Which
Not
one?
vertical.
Because
Talking about?
7.
of the fact that it's air. Air only moves
Horizontal.
in a transverse way. We draw it graphically like that, but it only works as a standing compression wave.
I didn't
So-
do 7 or 8. Oh my god.
Wait, so are loads antinodes?
No. Antinode, so here's the story,
That needs to be a long one.
okay? So let's say you have something like this, okay?
That's how I remember.
So these here
This
Yeah.
one would be
are gonna be
4.
your
A
antinodes.
would be 4.
So they're like minimums and maximums.
Yes,
So there's 2 antinodes.
and you would have 3 nodes.
Why don't they just
So
call it
you
nodes
always
or
have,
modes?
Isn't it
you always have one
on
more
this one?
Sorry, I couldn't.
node than antinode.
So what's a mode?
Mode is your harmonics, okay? So mode means the same thing as harmonic, because we're with the terminology, okay? So this one,
Or is it
okay,
horizontally?
here, so if you look on
Here, I
this,
should
so if you back up to question number 6,
transfer wave or something like that.
okay, if you look up at question number
So if you
6,
double frequency, you should double the
That's
amplitude,
okay.
right?
That is so good
Don't
thing I caught
start.
that. That's like
Okay.
a whole 4 points.
So on question number 6,
Yeah.
okay, that would have 3
antinodes.
Yes.
Antinodes.
And
4
two-
nodes.
Four. Okay.
Where's
okay,
four
I see.
nodes?
The 4, your nodes are the point where they don't,
Oh, that's where it's at, like
Yes.
middle.
yes,
That's it.
So antinodes is just whatever it's like at the top.
yes.
And on that one, you're doubling the frequency, so you're doubling the antinodes, right?
So do you count the top and the bottom, or just the top?
Just like that whole thing right there is one antinode.
Okay.
Oh, okay.
So if it only gave us one wave, right, and not the harmonic
Yeah, so
side,
if you had something
still have
like
one.
this, okay,
That's one.
that would be one antinode and 2 nodes.
Oh.
Okay, I have you, but what is a mode?
Okay, mode is the same thing as your harmonic, is like half the number of wavelengths. So this would be one mode. That's like your simplest, actually your simplest harmonic is when you have one standing wavelength like this. So
So
this
that's
would
two
be
modes.
one mode.
Wait, so how is the top left one mode, the bottom right is one mode?
I'm sorry.
Two. That the bottom right's two.
This has 2 modes.
Okay.
This has 1.
Gotcha.
Wait, so is
Yeah.
the mode and the antinode the same?
Yes.
So
That always-
it's
okay.
every football is a mode.
Yeah, if you want to think of it that way,
And
yes.
every osprey,
Every osprey is a
And-
mode.
And every donkey is,
every
anyway.
donkey,
Is it?
Wait, so I'm okay.
That makes sense.
Got it?
I'm
Yep.
Okay, yeah, the terminology gets weird.
Yeah. So it's
What is a harmonic?
Oh.
That's when it gets loud. How about that? Okay, let me hand out the lab.
Harmonic is all about how you.
What is a sound?
All situations. So, back in the day, there was a movie called The Beverly Hillbillies. Okay?
I've heard about that.
And the lead-in song to The Beverly Hillbillies was this song right here. It was called The Ballad of the Beverly Hillbillies. So let me kind of play this so you have an idea of what it sounds like. Now, if I could play the banjo, this is what I would be able to play.
we're drawing cards today for.
I'm not drawing cards, bro.
Okay, so you get the idea of the melody. Okay?
Is that you?
I feel like this is.
I like their
this is
bow
what we're trying
ties.
to think.
Is that what you used to look like back in the day?
What?
Now, you gotta listen to the words.
He said if I was able to play the banjo.
Is that you, Mr. Burkett?
Hold on. Just listen to the song.
I think that's him.
I feel like I no longer speak English. I can't hear
I need subtitles.
it.
Okay, so you have an idea of how the song goes. Okay? Without kind of repeating. Now, if I could, now imagine that I'm playing the banjo, which I'm not.
Why do we have to?
But,
Yeah, but you have a banjo.
but I do have a
Why
banjo.
do we have
Where'd
to?
that banjo go?
So what I did is that I rewrote the song, or the words to that song about gravity. Okay? So imagine that you're hearing that melody in the background as I sing this. So it's a little bit of audience participation. Okay? But here's the story. So imagine that imagine I'm playing the banjo that cool, which I'm not. And again, when I was born, God said, you can do math, you can do science, singing, not so much.
What about playing the banjo?
Oh, horrible. That's about it right there. Okay, so that song started coming, listen to the story, right? So this is how this is going to start. So there's 3 different verses. Stay with me here. So come and listen to a story about the search for gravity. Poor Galileo sat and explained how this can be. Then one day he was working in his lab, and up through his mind came a bubbling math. Equations, that is, solutions to the problem. He's dropping different masses to avoid a great disaster. Most folks said, the heavier one's going to fall faster. Aristotle said, well, that's the way it's got to be. So he loaded up his stuff and he moved to Italy. Leaning Tower of Pisa, that is, started dropping cannonballs. Well, now it's time to clearly state just what the facts should be. Mass is not a factor when things fall cause of gravity. You're all invited back again to Galileo's game, that independent of the mass, they always fall the same. Acceleration, rate of change of velocity. That's what we call it now. So that would have been much cooler if I could have played the piano and you could, or the banjo, and you all would hear that. But you get the idea of the first thing. Thank you very much. So that was one of the, stop. Okay. Zip it. All right.
Ovation.
So somebody, I need to do a quick conversion of Celsius at 71.2 degrees Fahrenheit into Celsius. I think some of your calculators do that, don't they?
Don't you have to like add 270 degrees?
Yeah, it's them weird. So I need
Just
71.2
ask Siri.
changed into
You know?
Celsius.
Do we have an equation for that?
About 20.
It's like no. Wait,
ballpark.
It's like 19 really close.
what's 71.2 degrees in Celsius? No, not that.
What's
No.
0.91?
18.85.
What is
18 point what?
Randomly guessing numbers.
I'm guessing. Don't worry.
Celsius 30 minus 130 Fahrenheit. Wait, what?
Just ask Siri.
Just ask what the temperature
What's
is in Celsius.
71.2 degrees in Celsius?
21.8 degrees Celsius.
I went the wrong way.
So close.
Okay, so
Wait, I thought 20 degrees Celsius was 72 degrees Fahrenheit.
Yeah, that's why it says
That's just a-
21.8.
That's an about.
yeah, so that's 71.2, so it's kind of close.
About.
Okay, so here's what you're gonna do. There's 4 different things that you have. So let's start with this. So over here on the back side of the lab,
That's PQ.
I've given you what, there's different tuning forks, and there are 320, 426.6, and 512. So what you're gonna do is that you're gonna go around like this and kind of break up into groups. So you're going to take that tuning fork, give it a wrap, lift that up,
The wallop.
Wallop?
Wallop.
Whoa, the scallywag.
okay, you hit that point. Now what you might do is kind of go up and down past that until you get that point. So what, you're gonna need 2 bits of measurements. You're gonna need to know, this is what's called a correction factor. This correction factor is over here on where you take 0.3 times the diameter of the tube. So measure the inside diameter of the tube. These all should pretty much be about the same. Make sure that it's in meters. And you multiply by 0.3. So, because what happens is that as that sound is vibrating within that column, when it hits the outer edge, it actually spreads out. It doesn't stay confined within that. So that 0.3 is a correction factor for that taking place.
Stop. Thank you.
Give him a wallop if I can.
Okay.
Wallop this man.
So then you're going to measure the length from the top of the tube to the top of the water. Okay? That's going to be 1/4 of the wavelength. Then what you're going to do is, once you get that, you're going to try and calculate the speed of sound using V equals lambda times the frequency. So you're going to know the frequency, whatever that number is, 320, 426.6, whatever that is. You're going to know the frequency. So on the front of here, where it's got determine the accepted value for the speed of sound from the following equation. This is where we need that number for temperature. So let's do this so that everybody's cool. So we're going to take 331
Which page?
plus, it's on the front of this page, so 0.6
Oh,
times, what was that temperature, 21.8.
yes.
So somebody take 0.6 times 21.8 and then add that to 331.
344.1.
340 what?
344.1.
344.1.
So that's the accepted value.
So that's the accepted value. That's what we should get for the speed of sound under these conditions. So what you're going to do is you're going to go through and you're going to take that 0.3, and this is where you're going to use this correction factor on calculating the wavelength. So to get your wavelength up here towards the top, you're going to take 4 times L plus 0.3 D. So the L is going to be, this is length, Louis, okay? So you're going to measure that length, okay? That's going to be your L values, uppercase L anyway.
L value?
you're gonna have the diameter of the pipe, that, you're gonna know that number, and then, again, you're gonna multiply by 4, because that is representing 1/4 of the standing wave of the pattern, okay? So, you're going to get an experimental value for the wavelength from this. You're gonna know the frequency, because that's what's gonna be stamped on the tuning fork. So then, from that, you're going to get a calculated speed. And then your experimental error is going to be based upon that comparison to 344.1. Okay, remember, your experimental error is theoretical minus experimental divided by theoretical times 100. So basically, you're going to take that 344.1 minus that divided by 344.1 times 100. So you're going to have 3 known frequencies, okay? You're going to know 3, you're going to try and find it. Now, you're also going to have, down here at the bottom, you're going to have an unknown one. So on that one, you're going to try and figure out the frequency of the tuning fork. I'm going to have a piece of gray duct tape over it. You can't see it. The whole point is that you're going to try and find it. So with that one, you're going to reverse the process. You're going to know the accepted value for the speed of sound. You're going to measure whatever you need to measure, and then you're going to try and find the frequency, not knowing what that is. So you're going to have 3 that you know and 1 that you don't know. Now, over on page 2, on that back side of that front page, there's going to be 1 open tube. That's actually, I'm going to have that next door because that's the hardest one to hear. So, Morella, stop that camera for a second. We go get that. Okay, so with this one, this is the hardest one to hear because open ones, you don't get that really strong resonance like you do with an open closed system. So this is why this one I'm going to have you go next door so that it's a little bit more quiet so you don't have all the background noise.
Aren't the freshmen in there?
No, they moved out. I
He
can't.
would not go in there.
So what you're going to do is take this, hit this.
On Pop's head.
So what you have is a tube inside of a tube. So hold that on the end, and this is why it's kind of handy to have 2 people. And you're going to move that, and you're going to adjust that length. About like yayish. Okay? And then you're going to measure the length of this tube. Now, because this is an open one, this is going to represent half the wavelength. So imagine you have like, starting here, that wave is going to come down here like this, so that's going to be half the wavelength. You don't have to worry about the correction factor on an open one like you do on an open closed one. So on that one, you're going to measure that length, okay? So you're going to take this is how you're going to adjust that length. So you're going to slide this pipe out until you hit that resonant point where it gets louder. Then you're going to measure the length. That's going to be easier if you have 2 people where one person's holding the tuning fork and the other person is adjusting the length of these tubes until you hit that point. So then you're going to calculate a wavelength. From that, you're going to calculate the wavelength from there, and then on this one, you're going to use the theoretical value of the speed of sound, which we found to be that 344.1. Then you're going to determine a theoretical wavelength. So it's just wavelength times frequency equals lambda. So you're going to know what the frequency is. It's stamped on here. That's going to be that 523.2. So you're going to know the frequency. You're going to calculate a theoretical wavelength, and then you're going to compare that to what you got. So there's going to be a total of 4 different setups. You're going to have, 5. one open one, that's gonna be next door. Then you're gonna have 3 known tuning forks and 1 unknown tuning fork. So basically, rotate your way around. Got it? Good? Okay, let's go do science.